So now let's look at finding parametric equations for circles and related to that, ellipses. We've looked at just taking a Cartesian equation and converting it over. What would be the problem with that with circles? Let's take a look. Here's a basic circle, right? X squared plus y squared equals r squared, right? That would be a circle of radius r centered at the origin. And what I've told you could do with other equations is if you could write it as y as a function of x or x as a function of y. So here's the problem. A circle, y is not a function of x, right? It breaks into two functions. It fails the vertical line test, right? And it doesn't do you any good to solve for x either. If you solve for x or solve for y, either way, it breaks into a plus minus. So this approach for trying to solve for one variable and let the independent variable be t doesn't work. So what we can do, though, instead is take advantage of what we know from trig identities. So if we were to take x equal cosine t, y equals sine t. So that describes a bunch of points, right, for various t's. But there's something that's always true of sine and cosine, therefore is always true about x and y on this curve. We know from trig that sine squared plus cosine squared is 1. The Pythagorean identity, right? Well, on our curve, sine is y. So that means on our curve, y squared plus, and x is cosine, x squared equals 1, which is the circle of radius 1. So just by taking advantage of a trig identity, we're able to get the circle. And we can write it, I guess, in the more standard direction. X squared plus y squared equals 1. Now, what I'd like to do is talk a little bit about, well, what is the direction of motion on this and how could we figure it out? So let's draw a picture here of our circle. We know by the relationship that it's a circle of radius 1, so I know the shape. Now, which way does it go? Let's think about this. At time 0, where are we? When t is 0, cosine is 1, sine is 0, so we're right here. So you're right there at time 0. Now, we either go up counterclockwise or down clockwise. Well, let's think about what's going to happen when you start to plug in t's slightly larger than 0. So as we move forward in time, do we go up or we go down? Well, we could really just look at y, right? What happens to our y values right after t equals 0? Well, for t's slightly larger, let's think about this. Let's just draw a quick graph of what this would look like in yt space. So we'll draw a graph up here. So as we move forward in time, what's happening to these y values? Well, after time 0, the y's go positive. So after time 0, we're going to be moving up. So our t's are going to move into this quadrant until we get up to a y of 1. And then the y's start to go down, and then that's us moving, continuing. So following this graph of just what the y's look like tell us that we're going to head around this way. When we get to that peak at pi over 2, that's time pi over 2. Now this might look familiar to you because think about what we did. We parameterized. That's the definition, right? From the unit circle, x is defined to be cosine theta, y is sine theta. So our parameterization is actually the definition of how we measure sine and cosine on the unit circle. And so really t is, in this particular parameterization, t is theta, right? As we go around increasing theta, we sweep around that circle counterclockwise. So what I'd like to do now is play around with this, make some alterations, and see how we can alter this parameterization and get various circles with various types of motion. So let's take a look in Desmos. Okay, so here we have our circle that we were just looking at. And notice how I put this into Desmos. You could do this in your TI. You just switch to, you go into your mode, and you can switch from function mode to parametric mode, and you can put in parametrics. In Desmos, I think it's a little more intuitive. If you give it an ordered pair, because think about it, what is a parametric? It defines x as a function and y as a function. And that's exactly what you do. So just like you would be writing a point, you put in the x function and the y function. And then you have to give it some range of t values. So I just went 0 to 2 pi, so I would get the whole circle once around. Now, one downside to this is I don't get to see the motion. When I graph this, the whole circle's up there all at once. So we can fix that, though, by putting a limit on t. I'm going to only graph t less than a. And then I'm going to add a slider for a. And let's have a go from 0 to 2 pi. And maybe step by 0.01. And so by letting a, and we'll switch this so it only goes forward. Let me slow it down a little bit. So by limiting the domain, I've kind of tricked Desmos into showing me the motion, because it's only going to graph this up to t equal a, but then I'm increasing a. So here we see that counterclockwise motion as we go around. And so that was the thing we just looked at. What if we want to go the other way around? Well, one of the easiest ways to do that is to change the roles of x and y. Now think about this. In algebra, we learned that when you change the roles of x and y, you invert the equation. And when you invert this equation, you would make a mirror image along the line y equal x. So if I do that, that mirror image will be going around the other way. So I'm going to make x be sine and y be cosine. Now, it's still true that x squared plus y squared equals 1, right? Because sine squared plus cosine squared is 1. So it's still a circle of radius 1, but now we see we are going around clockwise. We also see that we're starting somewhere different, right? When we went counterclockwise, we started on the x-axis right here at 1 on the x-axis. Now we're starting here at 1 on the y. OK, so we can make circles go clockwise or counterclockwise. Now here's the really nice thing about parametrics is because x and y are defined independently, you are free to vary them independently if you like. So if I would like x and y to all be larger, if I want to make that circle bigger, let's put a parameter b in front. So b times sine and b times cosine. And we'll start b at 1. By shrinking or increasing b, I can make circles of various radii. And now this is much easier than in algebra where you had to remember, OK, if I'm working on the inside of the function, I do the opposite. If I'm working on the outside of the function, I do the intuitive thing. No. If you want your x's all be bigger, make them all bigger. Just multiply by whatever constant you want. Now I'm multiplying x and y by the same amount. So I'm getting circles of various radii. What if I did them by different amounts? Add the slider. Let's get the whole circle going here. Notice I've stretched by a factor of 1.8 in the x, that's the b, and I haven't done any stretching yet in y. So I've got an ellipse. Or I can, by changing the factor of stretch in the y, I can make any ellipse I want, or change x by any amount I want. So very simple to alter your equations. Very intuitive, direct manipulation. What about moving it? These are all centered at the origin. Well, what does it mean to move an object? It means to add or subtract an amount from the x's and y's. So let's say plus d. And I don't think it'll let me put in e because that's predefined. So we'll say f, and we'll add sliders for those. So there's my circle. D is at 1, f is at 1. Our center is at 1, 1. If I want to move it left or right, simply move it left or right, up or down, up or down. So I can actually generate any circle I want, center anywhere I like. If I make these factors different, they're ellipses. But I can make that thing anywhere I like. So here's a circle. Actually, my B and C are not quite exactly the same. Try and make it exactly a circle. And I've moved my center to x equal 2.6, y equal 1.7. So unlike all of that weirdness from algebra where you have to remember to subtract when you think you should add and all of that, there's none of that. If you want to go up, you add. If you want to go down, you subtract. If you want to go left, you subtract. If you want to go right, you add. So it's very intuitive working with parametrics as opposed to our Cartesian equations from algebra. And my recommendation as you get comfortable with parametrics is just to play around in Desmos or with your TI. The one thing with your TI is you don't have to do this little trick. It'll graph it with increasing t so you can see the motion. But the nice thing about Desmos is the ability to put in parameters and play around with parameters and see what effect they have on your graph. So as you're trying to get comfortable with parametrics, my advice is just to come in here and mess around with various equations. Just see what kind of graphs you can come up with.